Okay, so here is given a series parallel combination of a circuit. What we see here is a voltage source V, a resistance R1, then there is resistor R2 and R3, and the circuit is given as shown. So current I is indicated as shown, and there are two loop currents I1 and R2 as shown. So in this circuit, we see clearly resistor R2 and R3 are parallel with each other. And that's why we are talking about the series parallel circuits. R1, this resistor, is in series with the parallel combination of R2 and R3. Okay. So what we can see here, the parallel combination of R2 and R3 can be written as, to calculate its effective resistance, we can use this formula 1 over R parallel, where R parallel is the parallel resistance of the R2 and R3, is equal to 1 over R2 plus 1 over R3. And therefore, if you want to know the value of R parallel, it would be written as the reciprocal of this term. Okay, so R parallel, that is the parallel combination of R2 and R3, can be given by this formula. Once you know R parallel, you can calculate the equivalent resistance of this network, which is R equivalent, which is the sum of R1 plus R parallel. So R1 comes in series with the parallel combination of R2 and R3. So that is how you can calculate the equivalent resistance of this series parallel network. Now we move on to the next slide. And in this, we are given the example with the values of the circuit components. So R1 now has 1K value, R2 has 1K value, and R3 has 1K value. Now we have to calculate the value of the effective resistance of this network. So we will use the earlier formulas. That means we first calculate the value of R parallel by this formula. So 1 over R parallel is equal to 1 over R2 plus 1 over R3. And therefore, R parallel is equal to 1 over this term. And we know that R equivalent would be then sum of R1 plus R parallel. So it's time now to plug in the values of R1, R2, and R3 to calculate the final equivalent resistance of this network. So what you do here, you write 1 over R parallel, that means this formula, equals to 1 over R2, that is 1K, plus 1 over R3, that is again 1K. Therefore, R parallel is equal to 1 over this complete term. And after solving this, you get R parallel is equal to 1 over 2K, that means 1 over this term, which is equal to 500 ohm. Once you know the value of R parallel, you can then calculate R equivalent with this formula, which is R1, that is 1K, plus 500 ohm, which is R parallel. So total equivalent resistance of this network is 1500 ohm. So this is how you can use these formulas and a method to calculate the equivalent resistance of any series parallel network. You have to first understand what combination of the resistors are in series and what combination of resistance are in parallel. Now moving on to our next slide, we see now the voltage source is given a value of 1 volt, and you are having the resistance, all resistance, with a value of 1 kilo ohm each. Now the question to you here, we have to calculate current I1 and I2. So you see that when you apply a 1 volt voltage source to a network composed of R1, R2, and R3, resultant current I comes out of the positive terminal of this voltage source and it flows through R1. Then it is splitted into two branches named as I1, that is flowing through this loop, and then I2 that is flowing in this loop. So therefore, we are asked to calculate the values of I1, and I2. So to solve that, we know that R parallel is 500 ohm because we know the values of R2 and R3. R equivalent we also have calculated from the earlier point, that has been calculated to be R1 plus R parallel, that is 1K plus 500 ohm equal to 1.5 kilo ohm. Once we know the R equivalent, by applying the Ohm's law, you can get the value of total current into the circuit, which is I equal to total voltage V divided by total resistance R equivalent. We know that V is equal to 1 volt as shown over here, divided by R equivalent we just calculated, which is 1.5 kilo ohm. Therefore, total current flowing into the circuit is 0.66 milliampere. This is the current of I that is coming out of the positive pin of the voltage source. Or we can say this is the value of a current that is being sourced into the circuit. Now we know that this current I is equally splitted between two equal currents, that is I1 and I2. So this R2 and R3 as there. So now we know the value of I, which is 0.66 milliampere. But we are asked to calculate both I1 and I2 as well. So if we know the value of I, and if we know either one of the I1 or I2, we can get the value of another current I2. However, both I1 and I2 are unknown here. Only value of I is known. So how to determine or calculate value of I1 and I2? So to do that, we need to know the voltage across the equivalent resistance of the parallel combination of R2 and R3. So R equivalent, we know that is the parallel combination of R2 and R3. And we want to know the voltage across this parallel combination of R2 and R3. That is why voltage drop across the parallel combination of R2 and R3 is VR equivalent, which is this voltage minus the voltage drop across resistor R1, that is V minus VR1. In other words, we are applying the Kirchhoff voltage law here. So V minus voltage drop across R1 will be the voltage drop across R2 or voltage drop across R3. So VR equivalent will be V can also be written as VR equivalent equal to V minus I times R1. This voltage drop across R1 right over here is nothing but the current flowing through the resistor R1 multiplied by the value of resistor R1. We know that value of current is 0.66 milliampere and value of R1 is 1 kilo ohm. Therefore, we can calculate the voltage across the R equivalent, which is 1 volt minus I times R1, that is the value of current 0.66 milliampere multiplied by 1 kilo ohm. It comes out to be 0.33 volt approximately. Now we know the voltage drop across the parallel combination of R2 and R3. Once we know that, it means we know the drop across R2 and drop across R3. It's now easy to get the values of I1 and I2. So I1 would be again Ohm's law, voltage divided by resistance. So VR equivalent divided by R2 will be the value of I1. So that is the current flowing through this resistor, which is by plugging the value of VR equivalent, that is 0.33 volt, what we just calculated here, divided by 1 kilo ohm is the value of I1. Similarly, we can get the value of I2, which is again by Ohm's law, voltage divided by resistance, where voltage is the voltage drop across this resistor R3 divided by the value of resistor R3. So which is 0.33 volt divided by 1 kilo ohm is equal to 0.33 milliampere. Note that value of I1 and I2 both have the same value, that is 0.33 milliampere each. And by summing these two values, I1 plus I2, we get the total value, which we just also have calculated to be 0.66 milliampere with this formula. Now you can see we can also calculate the voltage across R1, R2, and R3. So voltage across R1 is VR1. You see this voltage drop. Voltage across R2 is VR2. You see this voltage drop. And voltage across R3, you see this voltage drop. So here again, we know the value of R parallel, R equivalent, and the current I from the circuit. Now, VR1 is again by Ohm's law, current multiplied by the resistance. Where the current is the total current multiplied by the resistance 1K. So 0.6 is milliampere multiplied by 1 kilo ohm is equal to 0.66 volt. Now, VR2 is this drop, which is nothing but VR3 is voltage across this drop. So this VR2 equal to VR3 will be V minus VR1. That's why we have written here. So V minus VR1 is nothing but voltage drop across VRQ, what we just calculated in our previous slide. So by putting the value of VRQ, which is 1 by putting the value of voltage V, which is 1 volt, minus VR1, which is VR1, 0.66 volt, we get the voltage across R2 or voltage across R3 to be 0.333 volt approximately. So this is how we can, by applying simply an Ohm's law, we can calculate all the voltages, currents, and the values of the currents and the voltages into the circuits. Similarly, we also saw how we can calculate the effective resistance of the series parallel network or series parallel circuit. So hope you found this model useful. If you did so, share it with others for a wider reach and stay tuned for more informative content like this. Till then, wish you happy learning.